Okay, let's talk about naive Bayes. So in the last video, we discussed, or we looked at Bayes' rule, which is the basis for naive Bayes. So that's what gives naive Bayes its name, is the use of the Bayes rule. In this, we're going to look at, specifically, we're going to look at Gaussian naive Bayes. So that's because it's based on the Gaussian distribution. And I'll explain what that means in just a moment. So I'm going to do the same thing. I'm going to walk you through the second part of the handout today, and I'm going to leave you with an exercise. And this one's a little bit more involved and involves a bit more calculation. So you'll have to get out the calculator for this one, and we'll take up both the exercises in the live class. Oh dear. I might cut that out or not. Okay. Oh yeah, and the background, by the way, I don't know if anybody remembers this character who used to have this background, but I'll give you a hint. It's from the 80s when people thought that this kind of thing was super cool and out there. Alrighty, so let's take a look back to the handout here. Section 2, Gaussian naive Bayes. Okay, so the examples that we looked at, I way simplified them. We had one feature or maybe two features, and they weren't even numeric. Normally, most naive Bayes systems can't work on non-numeric features. The Gaussian naive Bayes requires numeric features, and that's the one that we're going to look at first. So I got some imaginary data here for you. We are trying to separate cats from dogs. So our two classes are cats, and here's the table for cats, and dogs, and here's the table for dogs. I've named them all. And we've got two features. Again, we're just keeping it simple with two features, length and weight. So we're trying to basically categorize dogs versus cats by size, which probably, if you think about it, is not going to work all that well. But it'll work well for an example. So Fluffy here has a length of 40 centimeters and a weight of 9 kilograms or something like that. Butch has a length of 81 centimeters and a weight of 24 kilograms, and he's a dog. And what I've done is I've calculated the mean and the standard deviation for each of these features. And that's all you need to do. That's all the calculation that you really need to do ahead of time for the Gaussian naive Bayes. You need the length, for each feature you need the mean and the standard deviation. And you also need the mean and the standard deviation for the whole set together. So as you would expect, if the mean for cats is 40.2, the length, and dogs is 73.6. The mean for dogs and cats together falls kind of in between. Same thing for the weight, and the standard deviations are what they are. So these are estimated means and standard deviations. They're estimated based on the data that we have. So if we had more data, we would get a closer estimate of the mean and the standard deviation for the entire population of cats and dogs. Again, having more data is always better, but like I said, a little bit of data can work well here. Okay, so from this information, we can actually calculate the probability that a new example coming in. So a new example coming in would be an animal that we haven't categorized yet. We would measure its length and its weight, give that to the system, and it would output a classification. And it does it entirely based on the means and standard deviations of length and weight, plus a couple of assumptions. So the two assumptions that we have to make, the first one is not usually considered the naive one. The first is that the data is going to be normally distributed. So that means that, for example, if you measured the lengths of all of the cats in the world, that they would cluster around a mean value in this way. You would get this sort of this kind of bell curve, this normal curve. And I think you guys might have seen this before maybe in your probability classes, but I'm not sure. When data is normally distributed, you can say something about, you can quantify that distribution. So for example, the mean length of a cat is 40.2. So that would be here in the middle. So the highest probability weight, what this is measuring here, is the probability of getting that particular length. So the highest probability length would be 40.2. But also, if you look at the standard deviation, all of the 68% of all cats would fall between one standard deviation of the mean. So up here it would be 40.2 plus 4.6, which is 44.8. And down here it would be Oh, it's a harder one. 40.2 minus 4.6, 39.4.6, 35.6? So between 35.6 and 44.8, if I got those numbers right, 68% of cats would fall within that range. Something like 95% fall between two standard deviations, and so on. And you can actually, there's an equation that you can use where, given a length, you can calculate the probability based on the mean and standard deviation and the assumption of a normal curve. You can calculate the probability that a cat would have that length. And you can do the same for weight, you can do the same for dogs, and you can do the same for the whole data. So we assume a normal distribution, which is also called a Gaussian distribution after the mathematician Gauss. So if it's true, it means that randomly selected animals more likely to have a length and weight close to the mean, less likely further away from the mean. And I go through some of the things I just said right here. 35.6. Is that what I said? Anyway. So the assumption of a normal distribution for length and weight is probably true. But for other, because the normal distribution comes from the study of biological data. So specifically in the 1800s, studies of crops, when they were trying to figure out how to make agriculture better and how to really know for sure when, for example, an intervention like a new fertilizer has produced better crops. So that's where a lot of modern statistics comes from, is in those studies of agriculture and how to do kind of agricultural experiments. So like measuring the height of a stalk of corn or the length of the forearm of a human being or something like that. Those kinds of measurements are known to be normally distributed. So there'll be a mean, and the distribution around that mean will look like this normal distribution. Okay, so a lot of times this isn't the right distribution, but it still kind of works anyway. But you can also you don't have to base your naive Bayes on the Gaussian normal distribution. There are other distributions known distributions that might fit your data better. So most people would start with just ordinary data using Gaussian and may try other distributions. Okay. So the assumption for some variables, the assumption that it's normally distributed might be a naive assumption, but that's not really the assumption that gives naive Bayes its name. Okay. So here's an example. We're classifying a new example. We've got length 40, weight equals 15. We don't yet know whether it's a cat or a dog. So we use the normal distribution to figure out how likely it would be to find an animal of this length and weight, given that it was a cat or a dog. So we can estimate conditional probabilities from this table. So we look at the mean and standard deviation length for a cat, and we can work out from that the probability, if this was a cat, the probability of getting that length. So we're getting close to what we want. If you remember, what we want is the probability of a cat given the length and weight that we've got. But we're going to use Bayes' rule. We're going to try and figure out the probability of a cat given the length and weight. So we can figure it out for each individual feature. The probability of that length given if it was a cat, the probability of that weight if it was a dog, and we can also figure out the probability of that length if it was a dog and the probability of that weight if it was a dog. And I'm just giving you some numbers here. If you're wondering how sklearn would calculate those probabilities, well, it does it like this. But we're not going to use that equation. We're just gonna work with given probabilities just to get a flavor for how the whole thing works. And then you can get the overall probability. So the probability of just getting that length of animal based on the mean for all cats and dogs is this, and the probability of getting that weight is this. So based on the assumption that it's a normal distribution, we can use this crazy equation here to estimate what would the probability of getting that length be and that weight be, given that it was a cat or a dog, and what's the prior probability of that length and that weight. Okay, so how is this going to help? Well, it's going to help because so we want the probability. So if we're doing cats, right, we want the probability of cat given that length and weight. Pardon my chicken scratch again. And we know that we can get that if we can measure the probability of getting that length and weight if it was a cat, multiplied by the probability that it was a cat, the prior probability, over the probability of getting that length and weight. Okay, so this is the classification task. We want to know what's the probability that it was a cat given the feature values that we got. We know we're not going to be able to calculate this. We don't know how to calculate this directly, but we do know how to calculate this if we make some assumptions about the data. We know how to calculate the probability that we would get that length and width if it was a cat. The probability of it being a cat is easy to estimate. We just look at our data and we say, okay, 10% of them were cats, so the probability of getting a cat is 0.1. That's the estimate there. And here we're estimating the prior probability of length and weight. So I've just shown you that we can do it for a single feature. So we can get the using the assumption of a Gaussian distribution, we can get the probability of that length given it was a cat, and we can get the probability of that width given it was a cat. Now that's not the same as getting the probability of getting both of those features together given that it was a cat. And that's where the second assumption comes in. So we want to know this thing. What's the probability of getting that length and getting that width together if it was a cat? And what we've got is the probability of the length if it was a cat and the probability of the width if it was a cat. Okay, let's go back to the handout. So that brings us to the second assumption, and this is the one that gives naive Bayes its name, the assumption of feature independence. So what does that mean? You've probably met this idea before. When two things are independent, two probabilistic events are independent, it means that the one has no effect on the other. So the best example is like random number generators, like dice. So the example I give here is you have a 6-sided die and an 8-sided die, and you roll them together. What's the probability of getting 2 ones? I might even have those dice right here, being the nerd that I am. Here's a couple. So here's an 8-sided die. It's got 8 sides on it. Here's a 6-sided die. I roll these things together. Oh my God. Oh my God. Oh my God. Can I do this? 2 ones. I don't know if you can see that or not. I'll have to check it on that. I can't believe that just happened. So wow. I'm going to go buy a lottery ticket after this. So what are the probabilities that that would happen? Well, so in this case, we know that those two events are independent. Hang on, I just have to check that I put my camera back properly. Yeah, it looks like I did. Wow, that was cool. What we know is that despite what a lot of gamblers think, I don't know if you guys have ever been to casinos or whatever, but there's the roulette table where they spin the big wheel and there's, I think, 36 numbers on it. And people bet on a number or they bet on red and black and stuff like that. Then it pays out if their number comes up. They'll keep a board going to show you what the most recent numbers were, like that matters. So people will look at that and go, oh, well, 23 hasn't come up in a while, so I'm going to bet on 23. That's called the Monte Carlo fallacy, the idea that we're due for, I've rolled the die 100 times and I never got a 1, so we're due for a 1. Somehow it's more likely that a 1 will come next. That is a fallacy. Again, it's called the Monte Carlo fallacy because Monte Carlo is a famous gambler's kind of den. Every event is independent. It doesn't matter if you rolled the die 10,000 times and didn't get a 1. It doesn't make it any more likely that you're going to get a 1 this time. Maybe you have a weighted die, actually, in that case, in which case maybe you're never going to get a 1. Or maybe there's 2 6s and they didn't put a 1 on there. But anyways, the point is they're independent. So the probability of getting a 1 on a 6-sided die is 1 out of 6. The probability for getting a 1 on an 8-sided die is 1 out of 8. The probability of getting 2 1s together if you roll them both, since those events are independent, what the 6-sided die does has no impact on what the 8-sided die does. Because they're independent, you multiply those probabilities together. So there, I had about a 1 in 50, a 1 in 48 chance of rolling those 2 1s, and I did it, and it was amazing. Yeah. So that's what we do. This is a very simple calculation. If those two events were dependent on one another, if they were not independent, it would make this calculation much more tricky. So what we do is we just make a naive assumption. Let's just assume, let's pretend that our features are all independent of one another because we've got this, and we want this, right? So how do we get that? Well, just multiply them. So we multiply the probability of getting that length, given that it was a cat, times the probability of getting that width, given it was a cat, and we're going to naively assume that that's an estimate of getting the probability of that length and width together, given that it was a cat. And we can do the same thing with this. So that gets us this top probability. We can do the same thing. I need to do something about that with this probability. I think I can. There it is. I need the small pen. There we go. Fix that. There we go. So to get this, the probability of just getting that length and that width is equal to the probability of getting that length times the probability of getting that width. So we just multiply them together. And why is this naive? Because it's almost certainly not true. It's definitely not true in this data. How could it possibly be that the length of a cat is independent of the width of a cat? So, the weight of a cat. So that would be suggesting that if you had a cat that was, the longer the cat, it doesn't make any difference as to how heavy it's going to be. But those two things are obviously related. Height and weight are related. Length and weight are related to one another. They are not independent. So this is a silly assumption to make. It's a naive assumption to make. But you know what? It works. It still works surprisingly well, even if the data is not really Gaussian, and even if the data is not independent, which it clearly is not in this case. It still works pretty well. So we do our estimates this way. The probability of getting that example, which means that length and that weight, given that it was a cat, is these things are easy to calculate. If we assume it's Gaussian, we just multiply them together. And same here. The probability of getting that example, probability of getting that length and weight, is just those two probabilities multiplied together. And the probability of cat, which is the other thing that we need. Where's the equation? Oh, maybe I didn't ever write down the whole equation. The probability of getting a cat is just an estimate of the number of the cats in the training data over the size of the training data. Oh, here it is. Sorry, I was looking in the wrong direction. So we can use Bayes' rule. So the probability of a cat, given the length and the weight that we got, is equal to the probability of getting that length and weight if it was a cat, which we do by getting these two numbers, using that crazy equation, and then multiplying them together to get that number. And then we multiply it by the probability of a cat and the probability of an example, which we get of getting that example. And you can put in those numbers if you want. Here are all the numbers that you need. You put them together and you get approximately 0.95. Okay, so how would you do that? You would multiply the length times the weight of probability of length given cat times weight given cat. And you would multiply that by the probability of a cat. What's the probability of a cat here? So I'm getting lost in my data here. So we have 5 cats and 5 dogs. So the prior probability of getting a cat is 5 over 10, which is 0.5. And then we've got these numbers here. Maybe I can do this. Let's zoom this out a little bit. Move it over here. And let's go back to let's use a green pen this time. So we are working this out, this equation. The probability of it being a cat given the length and the width, the example, which is going to be equal to the probability of that length and width given that it was a cat times the probability that it was a cat over the probability of getting that length and width. So that's equal to, according to our naive assumption, the probability of that length given it's a cat times the probability of that width given it's a cat times the probability that it's a cat over the probability of getting that length of using all cats and dogs over the probability of getting that width using all cats and dogs. So the numbers that we've got that we need are all up here, plus the 0.5 for the cat. So we just plug in those numbers. So it's 0.087 times 0.029 times the probability of a cat, which is 0.5, over the overall probabilities there, 0.014. It's making little circles for me here, times 0.039. And I will leave that to you guys to plug it into a calculator, or maybe we should do it. Let's get the calculator here. So we've got 0.087 times 0.029 times 0.5. Okay, and then we can just do divided by 0.014, and then again divided by 0.039. That doesn't look right. All right, well, never mind. That's deeply unsatisfying. So it's supposed to equal, if my example was correct, 0.95, approximately equal that. But apparently it doesn't quite work. So I should have checked this before I started. Maybe I got my numbers wrong. So I just made up these numbers, full disclosure. I think I didn't put them in here. I didn't put them into an actual Gaussian formula. So if you're making up your numbers, it can lead to some weird wonky results. Probabilities should be between 0 and 1. So the fact that the calculator is telling us 2.23 here means that I've done something wrong with my numbers. So sorry about that. But anyway, this is the correct calculation. It was the probability of the length times the probability of the weight times the probability that it's a cat over these values here, probability of length, probability of weight overall. Yeah. Anyhow, I may post an addendum if I figure out what I did wrong there, or if I did do something wrong. But what I want to leave you with is this exercise here. So this is a different version. We're trying to figure out whether a patient is sick or healthy, and we're using their temperature and their two blood pressure numbers, the systolic and diastolic blood pressure numbers. So BPS, BPD, and T for temperature. And we used our training data to get the following. So the probability of that temperature, given that they were sick, is 0.8. The probability of that temperature, given that they were healthy, or healthy, that's a typo, is 0.4. And then the overall probabilities among all patients of getting that temperature, that BPS, and that BPD, and the overall probability that we see sick or healthy patients. We're in a hospital here, so we see a lot more sick patients than healthy patients. Okay, so I want you to try and use that data and use the formula above to compute the probability that they're sick versus the probability that they're healthy using the naive Bayes procedure. So we'll take that up next class, and maybe I'll have an answer for you about what went wrong with my example. But the procedure was correct. I just think I wrote down the numbers wrong in the handout. So whatever you end up with, just double check it, and even if it's not a number between 0 and 1, it should be okay. I think these examples work though. Okay, so this is the naive Bayes classification procedure in practice. Gaussian naive Bayes. Let's say you have a new example in 5 possible classes. You start with class A. You estimate the probability that each feature value could have come from class A, and you do that using the mean and the standard deviation. So the training phase here is very fast. It's just calculate the mean and the standard deviation for every feature 2 times. So 3 times, once for each class, and then once overall in the training data. Then you multiply the feature probabilities together to get this, the probability of getting that example, given that it was class A. Okay, and this is the big naive step, because we are assuming that the feature values are independent. Now, yeah, I also say here in practice, you tend to get numeric underflow because you're multiplying. Let's say you have 1,000 features or 100 features. You're multiplying numbers that are between 0 and 1. Every time you multiply, you get smaller and smaller and smaller. So you can actually end up going below the precision of your computer system, and you get numeric underflow. It bottoms out at 0. It just becomes 0. So often they use the logs. If you take the log, I don't know if you remember how logs work, but if you want to multiply 2 numbers, you can take the log of both numbers and add them, and then take the inverse log to get the answer. So they often work with log probabilities, which avoids numeric underflow. And then you multiply that by the prior probability of each class. And if you're using logs, then you use, if the prior probability is 2, 3, if you're using logs, you'll just add the log of that. And most classifiers don't bother with the denominator. So if you remember over here, here's the example. Both cats and dogs, so if we're trying to do probability for dogs, it'll divide by the same denominator. So most classifiers won't bother to compute the denominator. It's just extra work that they don't need to do because you're dividing every result by that same denominator. So they just don't bother with it. In practice, they just calculate this times this, multiply all those things together, They may not even bother to take if they're using logs, they may not even bother to take the inverse log. They'll just compute this step times this step, and then the biggest value, the highest result wins. So they'll do that for class A, then B, C, D, E, and the highest class wins, and they return the result. That's how they work in practice. Now we're not gonna do that. We're not going to program that ourselves. I have some code examples here for you, which I'll show you now. This one is pretty straightforward. So we're using the Gaussian naive Bayes classifier, which you get by importing it from sklearn.naive Bayes. You get the Gaussian classifier from there. There's a number of different versions of naive Bayes in sklearn that are based on different distributions. We'll look at some more next week, but we're just going to use Gaussian this week. So you just create a new classifier. There's no parameters to put here. There's just one Gaussian naive Bayes classifier for each set of data. Then you fit it, and then you call predict. And here I'm doing a little bit of a calculation. I'm looking at I'm actually not even splitting it into training and testing data here. I'm just looking at the accuracy on the training data. So I'm using the data set targets, and I'm comparing them to the predictions, which you get by calling the predict method. And I'm just telling you how many they get right or wrong. And the other thing I do here in this example is I use predict proba, which is another method that gets you the probability of each prediction. So you get a big array, which is a related array to the predictions, that tells you the probability, all the probabilities. So let's just run this thing. So what I end up with here is there were 569 points. I mislabel 33 of them. So my error rate is 33 over 569. So 0.06, let's call it 6% error rate. And then I looked at the low confidence predictions. So low confidence I defined as being the probability was less than 9. So I did gnb.predict proba. Whoops. There we go. Predict proba, like that. Oh, right. I have to give it dataset.data, like that. So what that does is it comes out with the probabilities for each class. So there were two classes here in the breast cancer data set, malignant or benign. And so this is the probability, that's a 1, that it belongs to class 0, and the probability that belongs to class 1 is tiny. So it's 1 times 10 to the negative 144. So that's a classification for, I believe, that might be malignant or benign. Here's an opposite classification where the probability was really high for this class and really low for this class. So what I'm doing is I'm going in there and I'm showing the low confidence predictions. So low confidence is where oh yeah, and then I do max axis equals 1 here. So what this gets me is I want the maximum value, so the one that it actually used to create the prediction. So this gives me the probability of the positive prediction, the predictions that it used. And you can see a lot of them are 1s. Some of them are a bit less than that. Some of them are actually kind of low. Like that represents a low confidence prediction. So then I'm just looking at those probabilities, and I'm looking at the correct targets for low confidence predictions. So that's, I did low confidence equals probabilities less than 0.9. I just picked that number arbitrarily. I decided that's a low confidence prediction, and we get the Boolean array with occasionally a true in it, like that. And then I use that as an index into the predictions and into the targets. So this is what it predicted in these low confidence predictions, and this is the target, and these are the probabilities for those low confidence predictions. So you can see 1, 2, 3, 4, 5 mistakes out of 14. So the error rate for the low confidence predictions is much higher than the error rate for overall, which makes sense. So I'm just investigating a little bit there. The other thing that I wanted to do here is I wanted to show you, I have two other things to show you. Just like for the other classifiers, I wanted to show you how naive Bayes forms decision boundaries. I don't have any parameters I can tweak, so I've done something different here. I'm showing you the training data, and these are the predictions that it makes on that training data. So it tends to, if anything, naive Bayes tends to underfit. It doesn't overfit. It produces these kind of smoothly curved, overlapping decision regions like this. And then what I've done here is I've used the probability distribution where dark red is closer to 1 and white is closer to 0. So when it's classifying the red class, it produces this kind of probability distribution here. When it's classifying the blue class, it looks like this, and the green looks like this. So that's what the probabilities look like. And the hard boundaries here are formed at the point where, in this case, the green probability is no longer higher than the blue probability. On this side, the blue is higher. On this side, the green is higher. So that gives you kind of a full picture of everything it's doing. And like I said, you end up with these curving decision boundaries. If you want to look at how naive Bayes compares to the other algorithms that we've looked at, here's a graph that does that. So again, here's the training data. Here's a decision tree overfitting, potentially, the training data with minimum leaf samples is equal to 1. And here it is no longer overfitting when minimum leaf samples equals 5. Here's k nearest neighbor with k equals 1 overfitting, and then k equals 15 not overfitting. And here's naive Bayes. We only have one output of naive Bayes. But you can see that they're all kind of, if you look at this one, and this one, they're all kind of similar to one another. So they end up in kind of more or less the same place, but a little bit different. So each algorithm has its own kind of idiosyncrasies and its own way of looking at the data. Anyways, that's it. We'll talk about the assignment in class as well, but it's like I said, it's pretty straightforward. If you did the decision trees one, I would advise using the same data set and just plugging in. You can just copy and paste your file and change it to Gaussian naive Bayes instead of the decision tree. You only need to do one run, although you should do multiple versions of that run with different training and test sets and come up with the average. And then I want you to compare them to compare that run. How well did naive Bayes do compared to decision trees and k nearest neighbor? Okay, so we'll talk about the assignment in class, but you can take a look at it. It's up now, assignment 2A. And I'll see you guys in class.